Hi, so in this video we're going to talk about empirical formula and what that is. So first we'll go over a couple of definitions. The empirical formula gives the relative number of each element present in a compound in the lowest whole number ratios. So what I mean by this is the subscripts on the atoms written in the compound have to be in the lowest whole number ratios, and we'll see examples of that very soon. This is just for your notes. So the molecular formula gives the exact number of each type of atom in a molecule. So an example of empirical formula can be something like CH4, where 1:4 is the lowest ratio. It could be something like N2H or O5, where 2 and 5 are in the lowest whole number ratio. So it doesn't have to be 1 because we can't divide this by 2 because 5 cannot be divided by 2, right? So they just have to be lowest whole number. So they have to be, you can't write 5/2 or 2.5 or decimals. They have to be whole numbers, and 2 and 5 cannot be reduced any further. Other examples could be like N2O, or 2 and 1. We have just a 1 and 1, like an FeO or Fe2O3. All these are empirical formulas because they have lowest whole number ratios of terms. So the empirical formula can sometimes be the same as the molecular formula. What example of that? So molecular formula examples are things like N2O4, where this can be reduced to NO2, but the actual molecule present has N2O4. Other like C6H12O6, which is the formula for glucose. This is just CH2O if reduced to lowest terms, but this is the molecular formula because it is not in lowest terms yet. And examples are all empirical formulas, right? So if you actually have a molecule of NO2, imagine that's an NO2 molecule, right? This is the empirical formula and the molecular formula, right? But only if the molecule is an N2O4 that looks like this somewhat. This has a molecular formula N2O4, but that's not the empirical formula. Sometimes the actual molecule can automatically be in simplest whole number terms, in which case you don't have to. That is both the empirical formula and the molecular formula. That's not super important to know or understand. It's fine. We just have to know how to get from an empirical formula to molecular formula and vice versa. So the empirical formula for this would be CH2O3, C2H6F, because we're dividing all of these by 3 to get it to lowest terms. We're dividing all of these by 2 to get it to lowest terms. We can't divide by 4 because 2 divided by 4 will be 0.5. Here the greatest common divisor is 2, so this would be P2O5. And we can't divide by 4 again because 10 divided by 4 would give us a decimal number. And then this is already an empirical formula because we cannot divide 5 by 2. That's a problem. So how do we go from percentage to empirical formula? Now, I've used this kind of table here, and we did a couple of examples in class. So I'm going to do different examples just for extra practice. You don't have to. This doesn't have to look exactly like your notes. This is just to make sure you understand how we do empirical formula. So let's use this example. We have 52.93 aluminum, 47.07 oxygen. So element is aluminum and oxygen, and we have 52.93. Oh, it disappears. 47 point 0.07 aluminum. Oh, came back. Jokes. Okay. So, interesting, you'll see here that the mass in 100 grams is the same as the percentage. Because, what does percent actually mean? If I say 52.93% of aluminum, that means I had 52.93% translates to over 100. So, if I say 52.93%, that means if I had 100 grams of the substance, 52.93 grams of that would come from my aluminum, and 47.07 grams of that would come from my oxygen. So these percentage values directly correspond to the mass in 100 grams. Now I have to find number of moles. How do I find number of moles from the mass? And we're going to use the formula number of moles equals mass divided by molar mass. And so we need the molar mass of aluminum and oxygen. So let's look that up on our periodic table. Aluminum is 26.98. Oxygen is 16. So we're going to write that here, 26.98, 16.00. And we're doing number of moles, we're doing mass divided by molar mass. So 52.93 is the mass. I'm going to divide that by molar mass, and that's going to give us 1.96 moles. The same way here, we're going to do mass 47.07 divided by molar mass 16.00, which is 2.94 moles. And then we have to find our mole ratio, which is trying to, so basically, we basically have our answer already. We can write AL 1.96 O2.94, but this doesn't look very, good because we have decimals in it. When they're this close to whole numbers, you can automatically round to AL2O3, but that's not always the case. To make sure that this is actually what it is, we are going to divide both of these by 1.96, just like we take the lowest common, the greatest common denominator and divide to find our empirical formula. We're just going to divide by 1.96. And in this case, if we divide both by 1.96, I have 1.9.6 here. And we're just going to divide by the smallest number. What is 2.94 divided by 1.96? That turns out to be 1.5. But this still doesn't look right because now we have AL101.5. And to get rid of the 1.5, we're going to multiply this by 2. Because if we multiply a 0.5 by 2, we get a whole number. And this does actually correspond to what we would have got if we had rounded in the first place. So this is the correct answer. The formula is AL2O3. So we're going to do one more question for practice, but we'll go a bit faster. And again, like I said, I apologize. We need an extra column here because there's 3 elements: carbon, hydrogen, nitrogen. We're going to write our molar masses: 12.01, 1.008, 14.01, and hopefully we've done these enough that we can know them without looking at a periodic table. That's the goal. That's the eventual what it means to be a chemist, if you will. So as I can see, I'm just going to take the percent and substitute those numbers right into our mass in 100 grams. So we're not going to worry too much about what we're doing there. To find number of moles, I'm going to do mass divided by molar mass. One or two decimal places is enough here, just because we are going to be rounding and dividing stuff outside anyways. So 16.017, which is basically 16.2, but that's fine. Again, mass divided by molar mass. Okay, so I basically sort of all have my answer, but it's not, doesn't look very nice because of all these decimals, and so I'm dividing everything by 3.2, which is the lowest number, to get an actual answer. So I do divide by 3.2, divide by 3.2, divide by 3.2. This is 1, this is 1. What is 16.017 divided by 3.2? And we get 4.97, which we're going to round to 5. So our actual formula is now converted to C1H5N, which is the empirical formula. So hopefully we've understood how to calculate empirical formula. And one more thing that I will mention is a sample of oxide of nitrogen is found to contain 30.4 nitrogen. So when you're drawing our table, we have nitrogen. Our mass in 100 grams is going to be 30.4 grams. Our oxygen, we're not explicitly given a percentage for oxygen or mass for oxygen, but we know that it's an oxide of nitrogen. That means the compound has only two elements, nitrogen and oxygen. So if nitrogen is 30.4%, you can do oxygen, you can calculate oxygen to be 100 minus that value, which is 69.6 grams, which is just 100 minus 30.4. And you can continue. Again, you have to calculate number of moles. You do 30.4 divided by this divided by this, find mole ratio, etc., etc. I'm not going to go through all of that, but this is how you calculate if one is not given to you. All right. So I will see everybody in class.